Everyone, it's Dane Sandick. I'm Director of Research with the Institute for Catastrophic Loss Reduction. I'm joining you from Ajax, Ontario. Welcome to the September 2024 Friday Forum. Believe it or not, this is the 222nd webinar in our long-running series. If you're interested in our previous webinars, you can check them out. They're all posted on our website, both presentation slides and YouTube recordings. I'm hosting today, and if you're a frequent attendee, you'll probably be familiar with Dr. Keith Porter, who's our usual host. Dr. Porter is speaking today, so I'm hosting on his behalf. And also, the project that Dr. Porter will be talking about today was a larger project that I had a role in as well, and we'll summarize some of my work as well at the end of the webinar. This is actually the second webinar in a row that we've had Dr. Porter present. Last month, Dr. Porter presented a special webinar on some of his initial findings from the Jasper wildfire. So Dr. Porter had the opportunity to visit the town of Jasper with a group including Fire Smart Canada and others, and to inspect some of the damage and experience there, and provided a initial summary of its findings there. That webinar is available on our website, as well as both a YouTube recording and presentation slides. Next month, on October 11th, Alison Bird of Natural Resources Canada is going to tell us about the rollout of Canada's new earthquake early warning system. This is a system that, among other things, will push an alarm to your phone if an earthquake is in progress and the shaking is approaching you. This system will give the public a few crucial seconds to take protective action before they experience the impacts of an earthquake, including stopping elevators, preparing themselves for the impacts. So this is a webinar you'll probably be interested in checking out. So watch your inbox for a note from Tracy Waddington about that webinar. So today, Dr. Porter is going to be talking about the cost effectiveness of above code wind design for buildings. He's going to show us that above code design costs society less, results in lower costs to own and operate buildings over time, such that the cost of investing in wind protection the benefits outweigh the cost. This is part of a larger project that I was involved in, as I mentioned before. This is a project that was sponsored by Standards Council of Canada. It was related to the release of a standard on wind protection for Part 9 buildings called CSA S520, which is available. You can Google CSA S520 2022, and you'll find the standard published by CSA Canada. And there was two parts to this work. One part was Dr. Porter's BCA benefit cost assessment work, which he'll talk about in detail. And the other part, which I'll summarize very quickly at the end of the webinar, was a understanding of barriers and opportunities to implementation of the recommendations in CSA S520 that involved interviewing experts in the field, code development agencies, and so on, to give us sort of next steps to implement the recommendations in CSA S520. So before I pass it over to Dr. Porter, a quick overview of our agenda. The webinar is going to be about 90 minutes. Keith will present for about half of that time. There will be lots of time at the end for discussion, about 45 minutes for discussion. We'll ask that you enter questions into the Q&A box anytime throughout the webinar. We'll collect the questions, enter as many questions as you like, and I'll do my best to ask questions in the order that they were received. If we get a lot of questions from any individual, we may skip past them and come back to additional questions, depending on how many questions we get. Also, the webinar is being recorded, and we'll post both the slides and a video link within the next few days on the ICLR website. So feel free to share that with colleagues or refer back to it if of interest. And again, before I pass it over to Keith, just a reminder that on October 11th, we'll hear about the work at NRCan on the earthquake warning system. And with that, I'll pass it over to Dr. Porter.
Thanks, Dan. Okay, so I'm going to speak for the next half hour, 45 minutes or so about the benefit cost analysis part of this standard that Dan told us about. The research that I'm talking about today benefited both from coordination by Dan and from participation by 21 members of a stakeholder group who attended meetings, and they provided feedback and advice. So we thank them. All right, some motivation here. Canada has a history of costly storms. Wind damage contributes about a quarter of the losses in its costly storms. For over 100 years, we've known how to design buildings to resist strong winds and tornadoes, but we haven't actually done so. We haven't actually designed buildings to resist tornadoes, partly out of an untested sense that it might not be cost effective to do so. Now, this work aims to test that sense, considering this new standard, CSA S520, the thing that you're seeing on your screen now. Now, the picture on the left shows that cover, the cover of the standard that I'm talking about today, CSA S520-22. That new standard adds some well-understood, well-accepted design features to small wood frame buildings like houses. Those features better ensure that the building transmits wind forces from the roof and the sides of the building where the wind pushes or pulls on the building down to the ground. A building that complies with that new voluntary standard can resist virtually every windstorm that Canadian weather can throw at it now and for the rest of its lifetime. It's a voluntary standard. The picture on the right shows the cover of the National Building Code of Canada. That encodes mandatory design and construction requirements. Canadian provinces adopt it or a close proximity to it as law. So its mandatory requirements, they're less strict than the new standard that's shown on the left. And because of that, buildings built to the voluntary new standard, they cost a little bit more than the buildings built to the mandatory National Building Code. But CSA S520 also reduces the potential for future damage. With those stricter requirements, you get less damage, less potential for damage. So CSA S520 helps to avoid future losses, which we can call a benefit of the new standard. We calculate the avoided future losses and say that's the benefit of the standard. So it has costs and benefits. The costs come up front at construction time, and the benefits accrue during the future if or when a building experiences strong winds. Now, my presentation today presents ICLR's estimates of the added costs, the benefits, and the benefit cost ratio of complying with that standard relative to the National Building Code. The benefit cost ratio is the benefit divided by the cost. Where the benefit is bigger than the cost, the benefit cost ratio is bigger than 1.0. The larger the benefit cost ratio, the higher it is above 1.0, the more desirable an investment, at least on a long-term average basis. So now you've got a sense of what a benefit cost analysis is. I'm going to tell you about the benefit cost analysis of this particular document. Let me first sketch out some of our baseline information scholars often call a literature review. There are generally three ways to estimate the performance of a building or a class of buildings in future disasters. If one has adequate empirical data, one performs a regression analysis of those data. That's what actuaries commonly use to estimate prices to set the prices for insurance. They use past loss data and they perform regression analysis and they say, okay, well, you have this kind of house in this kind of place, and in the past, this kind of house in this kind of place has experienced this kind of loss, so we're going to set the price based on that past loss. But in a lot of cases, we don't have sufficient empirical evidence to estimate benefits. When that is the case, we can create an analytical model that basically operates on theory. Most of what structural engineers do use this analytical approach. And if an analytical approach exceeds your resources for doing benefit cost analysis, then expert guessing sometimes kind of has to do. So these are the three methods that one might turn to. In my presentation today, I'm going to talk about the analytical approach, which is what I had to do. Analytical approaches often work like I'm showing here. You start on the left by defining the asset at risk at a very fine level of detail, meaning what does the house look like, and what shape is it, and what is it made of, and how are its parts connected together. Then we do a hazard analysis. That's that next box over from the left. And in this case, doing a hazard analysis means estimating how frequently and severely the wind blows on the building. Then you do a structural analysis. That's where you calculate the forces on the structural members, every beam, every column, every connection. We calculate the forces given that the wind is blowing with such and such a pressure or speed. Then, given member forces, we can calculate probabilistic damage to individual components in a damage analysis. What happens to the sheathing? What happens to the connections? What happens to the connection down to the ground? Then we can estimate the losses given the damage in what we call a loss analysis, such as the cost to repair the damaged building components. And we can calculate a variety of performance metrics from the output of all that analysis, such as benefit cost ratio, among other things. So how do we do the asset definition for this particular case? What evidence do we have for the asset characteristics of the kinds of buildings that we're talking about today? Well, in prior work with ICLR and with Dan, I compiled a stratified random sample of 102 houses across Canada, 11 to 12 houses in each of 9 communities, ranging from small to large and east to west. The data generally come from Zillow and from Google Earth Street View, and they include things like latitude, longitude, stories, square footage, beds, baths, year built, cladding, perimeter length, and area, and so on. The picture on the right just shows you what a Zillow listing might look like, where I could get all of that information. Then we move on to the hazard analysis. That's where we calculate how frequently and severely the wind blows. For that, I drew on 2 sources. There is an organization called PCIC that offers future straight line wind hazard. That is wind pressure that has 1 in 10 year and 1 in 50 year exceedance frequency. I made some, now the Pacific Climate Impacts Consortium, PCIC, they offer you estimates of future weather under various climate scenarios. I used a sort of a middling shared socioeconomic pathway that reflects 2 degrees centigrade heating. Now, Canada has already warmed 1.2 degrees centigrade over the period from 1961 to 1990, and 1.9 degrees centigrade above the 1948 to 2022 period, according to Environment and Climate Change Canada. So 2 Celsius seems reasonable, and if anything, perhaps a little low. So the PCIC data talks about straight line winds, the kinds of winds that we experience normally as weather comes through our communities. And it doesn't include tornadoes. To characterize the added hazard from tornadoes, we can draw on the Northern Tornado Project and from other publications. The Northern Tornado Project is a project that ICLR is helping to fund at Western University. The figure on the left shows the locations of tornadoes during the period 2019 to 2023, according to the Northern Tornadoes Project. The figure in the lower right showed Dave Sills's idealization of a tornado footprint. It's sort of this lens shape. We're looking down from space. It starts narrow, it gets wide, and it gets narrow again. That's going to be important later on. So each one of those dots has this sort of lens-shaped path on the ground when you zoom in very, very close. And of course, it's not always east to west. It'll have different orientations, but it'll generally have that kind of shape. We're going to need to know about the damageability of the different components in a building. not what sort of safe loads are that below which you can be certain that the component is going to survive, but we want to know the probabilistic capacity of each damageable component. We want to know, what is the wind speed at which there's a small chance that shingles are going to pull up, and what is the wind speed at which there's like a 50-50 chance that the shingles will pull up, and so on. I'm going to show a few examples of tests like that that give us this kind of information. This photo is of wind uplift tests of roofing shingles. Here's a table of roof sheathing damageability compiled by an American wind engineer, Professor David Pravat, for various combinations of roof sheathing and fasteners. And by roof sheathing, I just mean the plywood or the oriented strand board that the roofers put on the roof trusses underneath and before they put on the shingles. So this is the pieces of wood that enclose the roof. Here are some tests of roof-to-wall connections. That's the connection between the roof truss and the top of the upper wall. So we've got some from laboratory tests by this person Chang, and there are some tests by Simpson Strong-Tie that we were able to draw on. That's a big manufacturer of structural components that we're able to draw on for this study. Now, the published data of roof-to-wall connections didn't cover everything we needed. We had to perform some roof-to-wall connection tests with what you're seeing here is a 2-ton engine hoist. We tested the toe-nailed connections that connect the roof truss to the top of the wall. You're seeing in the middle picture a couple of nails. That's two sides. This horizontal thing here, this horizontal 2x4, that represents the bottom chord of a roof truss, and there's two nails on one side and one nail on the other that connects it to the top of the upper story wall. That's these represented by these two horizontal 2x4s here. And the picture on the right shows this same connection after we pulled it apart using this blue engine hoist thing. So that gives us information about the capacity of this connection. The toe-nailed connection, like you're seeing here in the middle, fails at an uplift force of about 160 kilograms per connection. That's the force that 3 strong men could impose on this connection. So 3 strong men could pull the roof truss off of the top of the wall. The picture on the right shows this orange thing. That's a trussed screw that increases the connection capacity by a factor of 5. That's much stronger. So strong men could not pull this thing apart. It's much stronger, much more able to resist tornadoes, and add up all these orange screws around an entire building, and it adds about $190 to the cost of a house. So very strong for very low added cost. Now, for the loss analysis, that's where you estimate the repair cost given the physical damage. We draw on a variety of authorities. Here are some sources of roof repair costs, other residential repairs, the cost to replace damaged content, the cost of additional living expenses. That's when you're displaced from your home and you have to pay for a hotel or whatnot, and carbon costs. So these are sources for the dollar amounts that we apply to each of these sources of loss. Okay, so that was a sample of the literature we're drawing on. Now I'm going to summarize my analytical method. I defined the asset, the house, in terms of the building components that we normally use for structural analysis, with particular focus on the features that CSA S520 enhances. Those features are shown here. For example, there are things like thicker roof sheathing and different sheathing nails and stronger roof framing and connections, roof-to-wall connections, and so on. Step 2, the hazard analysis, requires that we characterize wind hazard in terms of the frequency with which various wind pressures get exceeded. The exceedance frequency for any value of wind pressure is the frequency of that wind pressure from straight line winds, that's the normal day-to-day kinds of storms that we see, plus the frequency of that level of pressure from tornado winds. And I'm graying out the math here and all the equations, just that the math exists and that there are equations, but I'm not going to trouble you with walking through the equations. Now, we want to design for strong winds without requiring that homes are built for winds that are extremely unlikely to experience in their lifetimes. Now, strong winds blow less frequently. Weak winds blow more frequently. Some wind pressures are extremely rare, but can happen during the life of a building, albeit with low probability. The building code has information about how strongly the wind blows in various places. It has a table, like the one that's shown on the left, that comes from that tells us how strong the wind is, that has a 1 in 10 chance of striking your house in any given year, and a 1 in 50 chance of striking your house in any given year for several hundred different locations around the country. Now, the picture on the right turns those 2 points, the 1 in 10-year wind and the 1 in 50-year wind, into a curve so that we can estimate how frequently other wind pressures happen at each of these places. Now, the climate's changing. The building codes table, this table in the building code mostly draws on the past for its data, but we want to know about the future. The Pacific Climate Impacts Consortium, PCIC, that I mentioned before, estimates future wind hazard and provides a table just like the one in the building code, but reflecting future weather. That was the one where I told you we're going to use the shared socioeconomic pathway that assumes 2 degrees centigrade. So I use the PCIC table for my calculation of straight line wind hazards. For tornado hazard, I calculated the exceedance frequency of various levels of wind pressure as a function of 4 things. Number 1, the tornado occurrence rate per 10,000 square kilometers. Number 2, the fraction of tornado track length that is EF0. That's the weakest tornado, EF1, EF2, etc. Number 3, the tornado footprint area. You remember that lens-shaped thing that has different lengths and widths depending on the maximum EF, enhanced Fujita rating scale. And number 4, the pressure distribution across the width of the tornado. A tornado has higher, or rather actually lower pressures and higher wind speeds at its center, and lower wind speeds, higher pressures at its edges. I'm going to skip over the math once again for the sake of brevity. It's just an application of a theorem that multiplies different outcomes by the chance of each outcome occurring to give you long-term averages. The third step, as I told you before, is the structural analysis, where we calculate member forces conditioned on wind pressure. Now, this is not a webinar full of wind engineers, so once again, I'm going to skip over the equations. Suffice it to say that I use the National Building Code of Canada's prescribed equations for the external and internal pressure on building components. I use that to calculate the force on every piece of plywood, every 2x4, and especially on the connections between them, the nails, the screws, the bolts, and so on. Those are the places where structural failures most commonly occur at those connections. Now, the fourth step, the damage analysis, requires characterizing the failure probability of each damageable component as a function of the force to which it's subjected. We define failure in a way that relates to the repairs, such as tear off of the roof shingles. Again, I'm going to skip over the math. I'm just going to say that curves like the one you're seeing here on the left-hand side of the screen, they're called fragility functions. They tell us that if you put a specific force into a connection or some other part of a building, there's a chance somewhere between 0% and 100% that the connection or whatever it is going to break. We make those fragility functions from laboratory tests like the one that I showed you with the big blue engine hoist, and that I showed you some tables of other people's laboratory tests. And now step 5 is the loss analysis. Once again, I've grayed out the equations, just know that they're there. You calculate the cost to repair a component category, like all the windows, as the product of 3 things: the failure probability per component, the probability of failure per window, times the number of components, the number of windows, and the unit cost per repair, the cost to repair one broken window. We're careful about double counting, and we also make some other reasonable assumptions about thresholds above which you just replace all the components, whether they're damaged or not. You sum over the component categories to get the total building repair cost. You add up the cost to repair the shingles and the roof sheathing and the windows and et cetera, to get the total cost to repair. You normalize by the building replacement cost to get what we call the damage factor. So you might estimate 10% repair cost, meaning 10% of the cost to replace the building, and that's the degree of damage from some level of wind pressure. Now we call a relationship between that percent repair cost and wind pressure a vulnerability function. We apply that vulnerability function to the building, to the contents, the additional living expenses, and to carbon, the value of all those things to get the total loss at any given level of wind pressure or wind speed. And lastly, we calculate the benefit cost ratio. Again, I've grayed out the equations. The point is that we integrate the vulnerability function and the hazard curve to get expected annualized loss. That is the long-term average annual loss from winds. That is to say, we calculate the loss given that a house experiences 75-kilometer-an-hour winds times the chance that it's going to experience 75-kilometer-an-hour winds. And we add that with 70 and 80 and 85, et cetera, to get the long-term average annualized loss. We do that under two conditions. Number one, compliant with the National Building Code of Canada, and again, compliant with CSA S520. So that's the long-term average cost under as-is and what-if conditions. The benefit, in terms of avoided future losses, is the present value of the difference between those two things, the present value of whatever is $100 per year of loss under as-is conditions minus $50 per year of loss under what-if conditions, and you add that up over a period of time and you account for the time value of money, and that gives you a present value of the benefit, the avoided future losses. The benefit cost ratio is just the benefit divided by the cost. Okay, so what I've shown you so far is a general method. Now I'm going to show you the results of when you apply it to new Canadian houses. I told you that I need to define an asset. Now I got one from a company that we often deal with, Doug Terry Homes. It's a very progressive builder. Doug Terry Homes provided us with drawings of a 3-bedroom, 2.5-bath that approximately matches the average newer house from that stratified sample I told you about earlier on with all the Zillow data. I've grayed out the interior features here, but the drawings show all the details, the materials, the geometry, and so on. I did what engineers call a quantity takeoff to calculate the cost to comply with CSA S520. Quantity takeoff just means, okay, how many square feet of roof cover and what is it you have to do differently to comply with CSA S520? And in this case, you use 6 nails rather than 4 for the roof cover. And you have to estimate the cost for each of those things. In this case, it's 3 cents per nail, and there are about 2,700 nails on the roof cover of this particular house, and that means that it adds $88 to the cost of construction to comply with CSA S520 versus not complying. You do that process for all these other differences between CSA S520 and the National Building Code, and you add in overhead and profit for the contractor, and you get a subtotal for the vertical for the things that resist the vertical forces from wind, the tornado uplift. The added cost is about $3,600. That's about $1.73 per square foot, and that $1.73 per square foot is consistent with findings from other sources that do approximately the same thing. So the vertical load path features of CSA S520 add about $1.73 per square foot to the cost of construction of a new house. Then I used the Northern Tornado Project data to make this map of tornado frequency. This map reflects 1,045 tornadoes in 4 years in 1 degree by 1 degree grid cells, 1 degree of latitude and 1 degree of longitude. The average rate over all of these places is about 1.25 tornadoes per 10,000 square kilometers per year. The maximum is about 9.5 tornadoes per 10,000 square kilometers per year. Now, here are the resulting hazard curves at 50 pressure levels. Remember, I told you that the code gives us 2 pressure levels, and I fit a curve to that. For many pressure levels, I calculated the frequency with which 50 different pressure levels are exceeded, given the straight line winds and the tornado winds. So each one of these rows is one of those 680 places in Canada that the code talks about. And each of these columns is the frequency with which various levels of wind pressure, those are the blue column headers, is experienced or exceeded. Here's an example of one of those places. It just shows the contribution to wind hazard from straight line winds and tornado winds in one particular place, Fergus, Ontario, which gets about 5 tornadoes per 10,000 square kilometers per year. The chart shows wind pressure on the horizontal axis and the likelihood on the vertical axis. Now, low wind pressures are more likely and high wind pressures are less likely. So the curve drops from the upper left, that's the more low likely low wind pressures, to the lower right, that's the less likely high wind pressures. The total is the black dotted curve. The green line is the straight line winds. That's the part of the hazard that comes from straight line winds. The red dashed line is the part of the hazard that comes from tornado winds. The picture shows that straight line winds, the green, coincide with the total wind hazard at lower wind pressures. That means that straight line winds cause most of the winds that exert lower pressure. But at very high pressures, the green line drops off and the red dashed line approaches the dotted line. That means that tornadoes cause most of the high wind pressures. In Fergus, Ontario, this chart shows we think the chance of a tornado is tornado wind pressures is low, but it isn't zero. Here are my vulnerability functions. Now, once again, this is loss as a fraction of the value exposed to loss. 0.5 on the vertical axis just means the repair cost is half of the replacement cost. The horizontal axis is the wind pressure. The solid line shows that a code compliant house starts to fall apart when it's touched by 0.5 kilopascal pressures. That's roughly equivalent to what an EF0 tornado imposes on a building. And as this building becomes a total loss around 1.2 kilopascals, that's about equivalent to an EF1, meaning that our current houses can't really stand up to any kind of tornado at all. They start to fall apart when touched by an EF0, and they're generally completely destroyed by the time if they're hit by an EF1. Now, the solid dashed line, or the dashed black line, represents the what if vulnerability function. It just starts to rise at 2.5 kilopascals, which is essentially a direct hit by an EF3 at its strongest point. So a CSA S520 compliant house can resist almost all the winds from almost all the tornadoes that strike Canada. I apply those vulnerability functions to the hazard curves that I showed you earlier for each of those 680 places in the building code. And then I tabulate all that. Here's the top of that table, and it shows each row is one of those places, and you see the latitude and the longitude of the place, the benefit in dollar terms, that's the column labeled B, and the benefit cost ratio, that's the benefit divided by the cost, which I showed you earlier was about $3,700. And here's a map of the benefit cost ratio. Any place with light blue or warmer colors, that's where the study is saying CSA S520 saves more than it costs, which is almost everywhere that most people live. So on a population weighted average basis, accounting for how many people live in all these different locations, CSA S520 saves an average of about $6 for every $1 of added cost. That is to say, we avoid $6 in future losses for every dollar that this standard adds to construction cost, or a net savings of $5. Now, there's a a number of uncertain variables in this mathematical model, and I performed a sensitivity study of those uncertain variables. Each bar on this chart shows the range of the benefit cost ratio when you vary one of these parameters from its lowest value to its highest value. The vertical line runs through the benefit cost ratio when you set every parameter value to its best estimate. It runs through 6 on the x-axis. The parameters are sorted in order with the topmost bar reflecting the parameter that most strongly influences the benefit cost ratio. The weighted average benefit cost ratio only dips below 1 for the least damaging values of a parameter called the internal pressure coefficient. Benefit cost ratio is fairly insensitive to all the other uncertain parameters that I've listed here. So some conclusions. First, I created a performance-based wind engineering analysis method to estimate the future wind vulnerability and losses to a particular house. I applied that method to an average Canadian house. In the kind of terrain where most houses live, the average benefit cost ratio is about 6 to 1. And when I say terrain, I mean suburban or urban environment, or places where there's a lot of trees around. The coefficient of variation of that benefit cost ratio is about 0.25. And that means that the 6 to 1 figure is uncertain within about plus or minus 25% when you add up all the places around Canada where you might have one of these houses. Which means that for almost all locations, CSA S520 is cost effective. It saves much more than it costs. Now, there isn't much data, empirical data, to validate the results, but my analysis roughly agrees with insurance claims data compiled by Cat IQ. Now, some limitations. First of all, I don't treat problems with inspection or non-compliance. These things matter, but they're separate questions. I don't treat differences in provincial codes. I only treat the difference between CSA S520 versus the National Building Code. And I told you that provinces adopt the National Building Code sometimes with minor differences. I don't treat wind-driven rain or water damage. And finally, I focused on the vertical load path for manageability. That's the forces that pull upward on the building from tornadoes. I didn't treat lateral forces, the side-to-side forces. This URL points to the benefit cost analysis, and you can download this for free at any time. And with that, I'm going to turn it over to Dan.
Great, thanks, Keith. And so hopefully folks on the line can see the Q&A box. Feel free to enter your questions. As soon as I'm done with my brief discussion here, we'll open up the floor for some discussion. So as we mentioned at the beginning of the webinar, Keith's work on the BCA, this was the major component of a larger project that was funded by Standards Council of Canada through 2023. Another aspect, so we approached Standards Council after, so just for a bit more context, Standards Council of Canada supported us for the past few years to develop TSA F520. There was a foundational document that we wrote back in 2018 that led to the contract to CSA to produce CSA S520. And when that was completed, we approached Standards Council to conduct the benefit cost assessment to support the standard. And at the same time, Standards Council asked us to also include some work that looked at the opportunities and barriers for implementation of CSA S520. So CSA S520 is a voluntary standard. It is not, to date, it is not referenced in regulation. It's not referenced in construction codes. So that means it's sort of a standalone voluntary guideline. Builders, code development agencies can use it at their will. And so that means that implementation is based on sort of the voluntary will of any potential user. And as such, we need some support to implement CSA F520 to test it out before it can be sort of rolled out more widely across Canada. And so to understand the context, to provide some more baseline information to help us understand where we need to go to implement CSA FY20, we interviewed 25 code, construction, and industry experts from across Canada, including professionals that were involved in writing CSA FY20, building code officials, code development agencies at the provincial and national level, influential industry associations, to get their feedback on the standard itself and what needs to be done to implement the standard. So I have here just some of the high-level findings from this work. The report is also available on the ICLR website, so you can check it out anytime you like. So first, the standard itself, so issuing the standard is sort of a formalization of our recommendations, or the recommendation to address high wind vulnerability in low-rise construction in Canada. So it was a helpful process to bring in experts to write something that was very formal that could be applied in the construction industry. Any recommendation for construction has to be backed up by a benefit cost assessment or impact analysis before it's considered for construction codes in Canada. And so Keith's work filled that gap. But the existence of a voluntary standard and a BCA to support that standard are, while they're critical, they're not sufficient for wide-scale implementation of sort of progressive building practices. So we're sort of at the beginning stage here in terms of wide-scale implementation of wind protection for buildings. Historically, new progressive changes in building practices take decades to implement. So if you think about greenhouse gas emission requirements that are now coming in many codes in Canada that are being more integrated into the National Building Code, there's decades of work behind greenhouse gas emission reduction, high performance buildings. Our timeline is much shorter. We're already experiencing significant impacts from high wind and multiple other extreme natural events, such that the cost of insuring these hazards is growing significantly. So our timeline is shorter. So we're hoping to make some progress on this topic more quickly than other progressive building practices in the past. There are several key groups that sort of have to come along with us to support implementation in Canada. That includes local building officials, provincial and federal codes agencies, and sort of reflecting the code development process. It's a very conservative process. It takes time to develop code changes. It takes time to work it through the system, sometimes many years. So the codes authorities, the code development agencies have to be on board. They have to sort of understand what we're proposing before we can get very far. National and regional industry associations, the building industry, the insurance industry, going from building company owners to trades to contractors. These are all important groups that have to understand the intent, the specific options that are laid out in CSA FY20 before they can consider applying them. And as such, training and education across the building industry is important. This is what we heard from our interviews, and also what we've come to understand working on this topic for several years. We're finding that the concept of resilience is still somewhat new in the building industry, and climate change topics that include resilience often get conflated with other climate change priorities like embodied carbon, operational carbon. And embodied carbon and operational carbon are very complex topics when it comes to design of buildings. It's important for us to educate the industry on the role of resilience, how it's different from these topics. In fact, in most cases, it's much simpler to implement resilience options than it is to address greenhouse gas issues in buildings, operational carbon, and so on. The approaches are much more straightforward, but there's a lack of understanding of what high wind resilience, wildfire resilience, what resilience means in the building industry. So, national wide-scale education training initiatives are an important part of implementation of progressive building practices. And we started some of this work. NRCan LEAP is also working along these lines as well. So we're hoping to make some progress, but it is a necessary component implementation of any progressive building practices, including those that are outlined in CSA S520. Also important to highlight, I think, especially for this group and ICLR membership generally, that when you introduce a set of progressive building practices like for wildfire, for basement flood, for high wind, what we've heard very strongly from the building industry is that voluntary implementation is important before we move to sort of market-wide implementation. We need to give the building industry a chance to pilot the options, to test them out, to understand the practical aspects of implementation. And that includes understanding like details associated with implementation of wind or wildfire resilience options. And to give you an example, we have a group of builders that we're working with, including Doug Terry Homes, that have highlighted in S520 certain prescriptive fastening options don't really align with what they do in the field. So for example, to give you a really specific example, CSA S520 gives options like using ring shank nails to fasten roof sheathing. What we heard from builders is that it's hard to source ring shank nails. The kinds of nails that they use in the field are different. They use nailing guns, framing nailers, and it's often hard to source ring shank nails for framing nailers. So can we find a way to work with industry to use the nails that they're already using in the field or slight modifications, longer nails, to meet the objectives of CSA S520? Voluntary adoption piloting gives us an opportunity to understand these details and refine them before these options are rolled out at the market-wide scale. Also, what we heard from our interviewees and from outside of the study from our colleagues in the building industry is that a tiered approach is important. And this follows what we've seen in operational carbon, for example, the Sept code in British Columbia. The way that CSA S520 is presented is as sort of a one option package. You apply the full standard or you apply nothing. And what we've heard from the building industry is that an incremental approach is important. So can we lay out these options in a way that allows them to sort of implement them over time? So can we outline a tier 1, tier 2, tier 3 set of options so that they can apply tier 1 in the near term, get used to those options, and then move on to other options as they better understand costs, risks, supply of materials, and so on. And that's also why piloting is important, to help us understand what the building industry can implement in the short term versus what requires more support for them to implement over time. I should note that ICLR and our partners, some of who are on the line now, are working to address some of these barriers that were identified in this report. We're working to identify piloting opportunities. We're working with the building industry to identify what we're calling sort of good, better, best resilience options to allow sort of for incremental implementation of wind protection and basement flood and wildfire protection. So we're trying to work with industry to identify their barriers and address those barriers. Also importantly is in terms of long-term implementation of resilience is understanding the objectives of construction codes. By and large, construction codes are designed for protecting occupant health and safety. Resilience includes protecting occupant health and safety, but also protecting property and protecting insurability of homes and so on. And this is not something that's typically incorporated into the objectives of codes. And we did submit a code change request with support from a lot of folks that are on the line I see today to propose the idea of a resilience objectives for the national and provincial codes in Canada. And we're actually encouraged by staff at NRC and code development agencies to submit that code change request. So we're trying to address some of these barriers, but in some, we've got a great step forward with CSA S520 with the benefit cost assessment that Keith mentioned, but we need to now work with industry to find opportunities to implement these options in the near term. And that concludes my summary of this report. So this report's available on our website, and we're happy to talk about it more in future. we'll move back into a discussion, and I see some questions coming in here online. So again, feel free to submit your questions. So we've got a question here from Christine, and I didn't get a chance to pre-read it, so give me 1 second here. Okay. Thank you, Keith, for the insightful overview. I admire your ability to provide engineering information in a way that even I can understand. The question is there a list of local governments, municipalities that have incorporated specific measures, such as requiring builders to use truss screws to address local hazard, despite the building code not requiring these options?
Well, I'll start to field that one just by saying you're very welcome, Christine. Thank you for the kind words, but I'm afraid I don't know the answer to that. If anybody does, it would be Dan. Dan, do you know the answer?
Yeah, so we do have some information to date. So first of all, in most of Canada, local governments cannot require measures that are outlined in CSA F520, especially those that relate to the structure of the building. But there are some municipalities that are moving toward incentive programs. So for example, Dufferin County, Ontario, which is centered right in the center of southern Ontario and has been the site of many high wind tornado events in the past, has an incentive program for builders. They provide, with support from ICLR, $4.50 for every improved roof-to-wall connection. And so that's everywhere on a building where the truss sits on top of a top plate. You would require some form of additional connection, a truss screw or a hurricane tie. So with ICLR support, Dufferin County is providing $4.50 for every connection that's improved. That works out to about $200, $250 per building. The way that has been implemented is at the building desk in the municipal office. Anytime somebody goes in with some plans for a new building, they're offered the incentive. And to date, that program's been running for a few years now, since about 2017. Hundreds of buildings, Part 9 buildings, agricultural buildings have taken advantage of that incentive, and I think now tens of thousands of additional connections have been installed through that program. So that's one example. There's a few other examples in Quebec. The city of Victoriaville has been running an incentive program that include some elements outlined in S520. And there's a few municipalities in Ontario that are also moving in this direction as well. So for high wind, not a huge number of cities yet. And one reason is because they can't require it because of building code regulation in Canada. But we're starting to see more come online. Many municipalities are recommending these options with guidelines for homeowners and so on, however. So thanks for that question, Christine. So keep your questions coming in. In the meantime, Keith, I've got a couple of questions. So a good part of your presentation focused on different methodology for conducting benefit cost assessment. You mentioned the analytical approach, which was your approach for this study, empirical versus expert opinion. Could you highlight, based on your experience, or maybe further, give us a little bit more information about why you selected this approach, the analytical approach for the study, and based on your experience, what type of approach tends to resonate more with decision makers?
So the approach that people like best, decision makers, insurers, etc., it's always the empirical one. You say, this is what actually happened. Here are 10,000 automobile accidents. Here are 10,000 heart attacks. Here are, here's the experience that actually happened in the world, and we can, you believe it because it's based on observations, and you can get all kinds of information from those observations. The challenge with relying on empirical data is that No one, there's basically two challenges for a condition like the one we're dealing with today. Number one, if you're trying to estimate the costs and the benefits of a set of requirements that nobody's implemented before, well, there's no, empirical database. There's no history. So you can't go to 10,000 houses and say, well, this one costs $5,000 more and this one costs $10,000 more. Partly because, nobody's built those buildings yet, and partly because even if they did, you wouldn't be able to get access to those costs, right? And also, um, what empirical data exist commonly don't get to the level of detail that we're talking about here. If you were an insurance company, you're a big insurance company, and you have a big database of policies, and you know where every house is, but the chances are good that you don't know much more than that it's a two-story house or that it was built in 1960 or something like that. You're not going to know details, even if there were tens of thousands of houses that had some of the features of CSAS 520. It was too costly for you to go out and collect the data. Oh, this one had truss screws and that one had, 6 nails per shingle. No, that's just too costly to collect all that information. So empirical data tend to be, well, they don't exist for new standards like CSAS 520 because nobody's built like that before. And even for past data, they tend to be very superficial. They don't have they don't distinguish the kinds of details that we need to be able to distinguish at the level of little fiddly details that you might put into a building code. So we're kind of forced to use either the analytical approach or the expert opinion approach. Nobody likes the expert opinion approach because it's just, well, Keith says it's this and Joe says it's that, and it's not repeatable. It's not scientific. The analytical approach, it deals with both of those problems. Analytical approach lets you use peer-reviewed science. You create mathematical models that anybody could create. You could hand off the mathematical model and somebody could vet it. It's just like science. You're doing an experiment in a computer rather than in nature, but the more closely your computer model seems to resemble nature, the more people believe it. The kind of performance-based engineering methodology that I showed you, that is the state of the art when it comes to earthquake engineering, when it comes to wind engineering, and a bunch of other kinds of engineering. So if you went to a structural engineering expert and you said, here is my performance-based engineering approach to this problem, that would be just like going to a chemist and saying, here's my chemical setup, here's my experimental setup. They can duplicate it, they can test it, they can peer review it. This is basically the gold standard for any kind of analysis for some new provisions or for some features of a building that are too fine to resolve with empirical evidence.
Great, thanks, Keith. Another question. I see several people from names I recognize from our member insurers on the line. So on the map on slide 33 shows the benefit cost ratios across Canada. In some areas were very good benefit cost ratios, some less so, but for the most part, most of the populated area, like you mentioned, of the country would experience benefits that would outweigh the cost of implementing these options. So I've been we were involved in a similar study for wildfire protection in Canada, and that study didn't just look at the direct cost to buildings or avoided insured losses. It looked at societal impacts of protecting buildings from wildfire. Thinking in terms of the insurers on the line, and what do these numbers mean for an individual insurance company? Say a company that wanted to consider, should we invest in protecting buildings if there's a tornado? Should we invest additional money to rebuild that home so it wouldn't be damaged in the future? What does that mean for our bottom line? Would you be able to translate this to something maybe insurers would find interesting?
Well, you can't go directly from the benefit cost ratio to the benefits and costs that insurers enjoy, right? So this is the long-term average. This is the present value of a savings stream that goes out over the life of a property, 75 years. And I think it may use a time value of money that's like 3% discount rate. And insurers, they're different. You know, they're not society. Society is not a monolith, and insurers are not the same as society when it comes to the benefits. Insurers tend to have a higher discount rate. Their cost of capital is more like 7% per year, because they can use their capital to invest in the stock market or something, and save more. So you tend to use a different discount rate when you're calculating present values when you're an insurance company. And unlike society, where you build a house today and it's going to be there for the next 75 years, and that's relevant to society. But for an insurance company, if they're insuring that property today, there's roughly a 90% chance that they're going to insure it next year, and a roughly 81% chance that they're going to insure it the year after that, and so on and so forth. The insurance companies tend to have a retention rate of about 90% per year. So the benefits to the insurer, they tend to be less than the benefits to all of society. I don't remember the exact, I mean, we've calculated this in the past. It's something on the order of a half. So you insure a property today, and if society is going to enjoy a $10,000 benefit, you, the insurer, are going to enjoy, I don't know, maybe a $5,000, $4,000 benefit if you're currently insuring that property. So we can actually, using the numbers that went into this benefit cost ratio, we can calculate the benefit to an insurance company. I'm not showing it in this map, and I don't actually remember whether we calculated the insurer's share of these benefits, but it's pretty straightforward to do from the data that went into creating this map. Now, also, if there are any actuaries on the line, they're going to be saying, we don't calculate present value of benefits. We calculate things in terms of the frequency of loss and the severity of loss. Well, we can do that too. With the information that underlies the data that went into this map, we can calculate the change in frequency and the change in severity in the in claims during your retention period of the property. So we can calculate that. Now, there's one little fussy detail in here. Some insurers, some people on the line are probably already thinking, but wait a minute. I may lose this policy 2 years from now, 3 years from now, 4 years from now, whatever. So yeah, this whole business of retention rate, that makes sense for the policy that I am insuring right now. But there's an upside, right? Somebody else does it, somebody else is currently insuring a house that 5 years from now I get. If it's got these features, then I'm going to get some benefit from that house too. So this sort of reduction from societal level to the insurer level, accounting for retention rate, that doesn't tell the whole story. The whole story is that you get some of my improved buildings, I get some of your improved buildings as people change around insurers. And when you add it all up, the benefit cost ratio, if you were to calculate benefit cost ratio, the ratio of my benefit, me being the insurer, to the homeowner's cost, the homeowner pays the higher price for the building. That's going to more closely approximate these benefit cost ratios. It's not quite going to reach these benefit cost ratios because of that difference in discount rate, but it'll get a lot closer.
Great, thank you. So two questions that have come up over the past couple of years since this standard was released. One is about the options that are presented in the standard. And for you to conduct the benefit cost assessment, you had to select a set of options that could be potentially incorporated into the average building and cost those out in order to understand what the potential cost of applying the measures are. Is it safe to say that a builder could take your benefit cost assessment study and the standard and select a different set of measures that equate to a similar cost of implementation, and would still the impact of applying those measures would still result in the same benefits. That's to say that the measures that you have presented or assessed in the benefit cost assessment shouldn't be considered to be the set of measures. These are just an example of potential measures that could be applied.
Yeah, no, that's perfectly reasonable. This is we sort of picked a middle case. I told you that we've got the sample of 100 buildings. Every building is unique. Even different buildings in the same development are each unique, and the cost is going to vary from one to the other depending on who the crew is you have on today and how productive they are, and so on and so forth. So the quantities that we calculated in this report, they're just sort of our best estimate for a typical case. And we've accounted for differences in wind hazard across the country. So the benefit cost ratio is going to vary from this building to that building, this set of choices versus that sort of choices. The house that we looked at had brick veneer up the first story and wood siding on the second story, but a different house is going to have different materials, and there's going to be a different benefit cost ratio. All that said, if a building is not too different from the case that we're looking at here, the benefit cost ratio isn't going to be too different from the one they're looking at here. You could, in principle, actually in relatively easy practice, we could have calculated benefit cost ratios for a bunch of different buildings. We could have looked at single-story buildings. We could have looked at different two-story buildings and come up with different benefit cost ratios. But I think that in the end, that's not really what people care about. I think that, when it comes down to a developer deciding, am I going to do this or am I not going to do it? They're thinking more qualitatively. They're thinking, all right, can I turn this into a marketing feature? I tell people my houses comply with CSAS 520. I'll get a general sense of how much that's going to cost me. I can tell the people, on average, overall, the benefit cost ratio of doing this is 6-to-1, or words to that effect. And that's what matters. The choice of whether to adopt the CSAS 520 depends on what your general feel for the benefit cost ratio is, as well as can you make a market out of it, and can your your laborers, your carpenters, and so on actually do it, and so on and so forth. All the fiddly details, they sort of matter, but I think the big picture is it's cost effective. It's highly cost effective. It makes new wood houses survive tornadoes, whereas they don't now. So yeah, at the fine level, we can calculate all those differences. But I think it's the big picture that really matters here. It's cost effective. It doesn't cost all that much, and it can create a building stock that survives tornadoes, whereas the one we have now doesn't.
Great, thank you. And maybe a related question. So you had a chart in your presentation. I didn't write down the number, but it showed the expected damage to Part 9 structures or homes that are designed according to building code versus S520. And yeah, there it is. So I thought this is an important chart because it demonstrates for the audience the incredible impact of applying the measures that are outlined in CSA S520. And that 0.5 kPa number, where the damages start to escalate for a code-built home, that is not a very severe wind event. We experienced those wind events across Canada, in the shores of Lake Huron in Ontario. Ontario is not considered to be a high vulnerability area, but on the long shores of Lake Huron in Ontario, we definitely get wind events like this.
Yeah.
So it's a good demonstration of the impact of S520. I think maybe one last question. I'm seeing questions, not too many more coming in here, but is about the impact of. Oh, sorry.
Do you mind if I respond to that? Because I mentioned David Pravat early in my talk. He's the Florida structural engineer and a bit of a visionary in the United States. He wrote an op-ed piece in the Washington Post a couple of years ago, and it was he who said he found a publication from the American Society of Civil Engineers. It goes back 125 years. American Society of Civil Engineers said tornadoes damage buildings, and this is how we can design them so that they survive tornadoes. So David said, this is not, it's not like we've never been able to do this. We've been able to do this for over 100 years, 125 years or so. We just chose not to. This chart shows the consequence of that choice. Our houses fall apart at wind speeds that are not all that uncommon. I was taught as a young structural engineer that it is unaffordable to design ordinary buildings to resist tornado. And I believed that without thinking about it. And it wasn't until recent years, until you helped create the CSAS 520 document, and David Pravat pointed out that this really isn't all that challenging, that people have come to realize we have been under designing and under building for generations, based on just assumptions that probably weren't ever valid. Anyway, I think that's what, when I look at this figure, that's what I see. I see a poor choice made generations ago that we could have made differently. And if we had done so, we would have had a much more resilient building stock.
Right. And that, as you often see, well, there's statements in construction code that say things like, well, you could build for these events, but we expect insurance will be in place, and the cost of insurance is less than the cost of constructing like this, so we'll rely on insurance. And increasingly, I think the insurance industry is being a little bit more open that insurability should not be assumed in the future, especially for, not specifically wind, but wildfire and urban flood and so on. We're starting to see some issues. One last
but before we move on, I want another point that relates to yours, and that is I often hear from builders and from other engineers hyperbolic assertions about the cost of building resiliently. I've heard from earthquake engineers, well, we could, if you made new buildings more earthquake resistant, it could triple the cost of construction. So you hear stuff like that, and you probe just a little bit and you find out that it isn't true. This is the marginal cost here is on the order of $3,000 for the vertical load path. That's on the order of 0.5% added construction cost, and smaller when you consider the purchase price. So we will often hear assertions that unsupported assertions about how this sort of thing is unaffordable, and it isn't. And I have heard you and others say before this business of it's cheaper just to insure. If insurance is priced correctly, it is never cheaper just to insure, right? I have there's a fairly famous earthquake engineer in the United States, a gentleman named Charles Scothern, with whom we've both worked for a long time, who likes to say the best insurance is steel and concrete, or in this case, it's wood and nails. And I think that's true here. So I'm sorry, I've interrupted you twice, but I think those are interesting points to make.
That's okay. That's okay. I think maybe also for the audience who just a note, like when you read CSAS 520, it is wood and nails. It's extra wood, extra fasteners. That's it. It's not a massive. We're not talking about building concrete walls or anything like that. Okay, sorry. One last question, and then I think we'll wrap it up. And that is, so you did conduct a sensitivity analysis. And one topic that you run into, and I think probably members of this audience have run into in the past, is you incorporate climate change impacts into the benefit cost assessment calculations using the PKIC tool that's available for everybody. It's a public tool. One issue that people run into is that the confidence in future projections for wind are not as high as for, say, extreme heat and other impacts. And if somebody has to bring this to a councillor or a mayor, and they push back and say, well, we don't really know about high wind, could you, I guess, define for us how important is climate change impacts relative to just our existing wind conditions in these calculations?
Well, actually, I didn't test the sensitivity of the benefit cost ratio to which shared socioeconomic pathway, I assume. So, but I did assume a fairly conservatively low change in future weather. I didn't assume the equivalent of RCP 8.5. I assumed 2 degrees Celsius heating. And as I pointed out, we've already, depending on what averaging period you're using, we've already experienced 1.4 to 1.9 degrees Celsius of heating. So I think the response, if somebody says, well, we don't really know what future weather is going to be like, and there's a great uncertainty, my response would be, yeah, but I made a very conservative assumption here, and it's still a benefit cost ratio of 6 to 1. The more skeptical you are of our ability to control global warming, the higher the benefit cost ratio is actually going to be. So if anything, this is a low estimate.
Great. Okay, thank you, Keith, and thanks again, once again, for the series of webinars and your ongoing moderating and hosting and organizing efforts for this series. When you sent that number 222, this is the 222nd webinar. I was kind of blown away, but we have been doing this for a long time at ICLR, and thanks to you for keeping this going and having such great presenters over the past few years. A reminder to our group that this webinar is recorded and will be posted along with the slides in the next few days. So you can go to iclr.org/workshops, and you'll be able to find this and all previous Friday Forum recordings there. And one last reminder to join us and Keith on October 11th to hear about the upcoming, to hear about the Natural Resources Canada's earthquake warning system that will be discussed on October 11th. And with that, we'll end it. Thanks again for your participation today.
Thanks, everybody. Bye-bye.